Hello and welcome back everyone. Today we will be talking about the parity space approach for fault diagnosis and fault tolerant systems. In safety critical applications such as aerospace, autonomous vehicles and industrial automation, reliable operation hinges on detecting and isolating faults before they propagate. For discrete time systems where states evolve in sampled steps, the parity space approach provides a systematic framework for model-based fault diagnosis. By exploring the redundancy between measured outputs and predictions from a nominal system model, parity relations are constructed to cancel the influence of unknown states and leaving only residuals sensitive to faults. So let us first write our model. X k plus 1 equals E x of k plus bu of k plus ed d of k plus ef f of k, and y of k, this of course equation number 1, and y of k is equals to cx of k plus du of k plus fd d of k plus ff f of k, and this is equation number 2. To apply the parity space approach, we don't just look at one time step. We consider the system moving over a moving time window from k minus s. So let's imagine we have a window. We have this window. Let us imagine that it goes from k minus s to k, and s is our moving window, and it is a design parameter to be designed. We have to design it. So let's start with writing. So y of k minus s is equals to c x k minus s plus du k minus s plus fd d k minus s plus ff f k minus s. As you can see, I haven't changed anything except for this checking the point at k minus s instead of k. Okay, let's substitute. This is 3. Let's get now y of k minus s plus 1. So the next point here, it should be cx k minus s plus 1 plus 1 plus du k minus s plus 1 plus fd dk minus s plus 1 plus ff f k minus s plus 1, and this is equation number 4. As you can see, we can substitute xk plus 1 with xk minus s plus 1. So we can substitute xk minus s, the solution of xk minus s, as in relation with equation number 1. So let's do this. So we now have y k minus s plus 1 is actually equals to cx k minus s plus c bu k minus s plus du k minus s plus 1 plus ced dk minus ced dk minus s plus 1 plus cef f k minus s plus ff f k minus s plus 1. And here are the terms. First term, second term, from substituting xk minus 1 xk minus s plus 1 by xk minus s, and this is this is the third term. I think I missed one term, cx plus bu plus du plus ced. No, the ced is k minus s, not k minus s plus 1. Yeah. So we have here the third term, and here the fourth term. And we have one more term from here that we forgot, which is fd dk minus s plus 1. Okay. Let's do the exact same thing for y of k minus s plus 2. Final answer is actually ca squared of x k minus s plus ca bu k minus s plus cb u of k minus s plus 1 plus du k minus s plus 2 plus caed of d k minus s plus ced d k minus s plus 1 plus fd dk minus s plus 2 plus caef fk minus s plus cef fk minus s plus 1, and finally ff fk minus s plus 2. As you can see from this trend, we can augment our matrices to be like y k minus s, y k minus s plus 1, and y of k, and they can be augmented to be equal to c ca till ca power of s x times x k minus s plus d 0 0 cb d 0 and till ca s minus 1 times b. Here off diagonal we have cb, and diagonal we have d. Of course we have zeros here, times u k minus s, u k minus s plus 1 till u of k, and then we have, and let's denote this matrix as HOS, this matrix as HUS, and then add plus FD CED till CAS minus 1 times ED, zeros here. Diagonal we have FD, our diagonal we have CED, and so we said diagonal we have FD, 3 here, 0 still here. And let's denote this matrix as HD of S. Of course, this is the K minus S, the K minus S plus 1 till D of K. Plus final thing is to have it terms of F. We augmented the matrices so that they are subject to X, U's, inputs, and disturbances, and finally you have to have the faults as well, which are same thing, F of F, here zeros, here C E F instead of C E D, so E F C F till C A S minus 1 times E F. Diagonal we have F of F, subdiagonal we have C E F, so we have F F here, and the rest are just zeros. And this matrix is of course multiplied with the faults of K minus S, Fk is S plus 1 till F of K. And let us add one more page, and let's denote this matrix as H F of S. To simplify, we can just write Y S of K equal to HOS times K of K minus S. As you can see here, HOS times K minus X minus KS times HOS times U of K times HDS times D of K plus HF of S times F of K. So let's write it real quick. Plus HUS US of K plus HDS S of K plus HF of S FS of K. Finally, let us design the residual, which is R of K. And as we know from the observer, we somehow want to make the residual to be the Y minus the Y predicted, right? So what we can actually do is write it as such. We can do a parity vector. This VS is, we call it a parity vector, and then we can do Y S of K minus H U of S times US of K. Why did I do it as such? So let's expand it and we will understand. So if we do Y S of K, which is this, let's denote this as 6, from equation 6 we can expand it here, ys of k to be, can denote this 6 r of k is equal to vs. Let's expand this y of s of k, so hos times xk minus s plus hus us of k plus hds ds of k plus hf fs of k, and of course minus hus times us of k. As you can see, subtracting this term, we can remove the effect of the inputs, and what's left is r of k is equal to vs times hos xk minus s plus hds ds of k plus hf of s fs of k. Now the residual is function of three things. First is the states, second is the disturbance, third is the faults. So how to remove the effect of the states is to make sure to add more condition, to add a condition. So this plus conditions we might say. So the first condition is that v of s times h of s should be 0. So we should choose the parity vector such that v of s times h of s should be 0. So now we can do what? We can do the residual signal to be v of s, since v of s times h of s equals to 0, so we can just remove this. So v of s is times h d of s times ds of k plus hf plus times fs of k. And now the residual signal is affected by both disturbances and potential faults. If this design is satisfactory with you, you should design the parity vector such that vs times h of s is 0. And this is, I believe, it's enough. But if you have a lot of disturbances, you can add the condition at the following condition. So you design the parity vectors such that hos and hd of s are both equals to 0. And from here we decouple the effect of disturbances from the residual signal, and the residual signal now is equal to v of s h f of s times fs of k. But you have to add for this this condition that v of s times h of s is not actually to 0, so that you can get the residual signal to be affected always and only by the potential faults. This is the session for today. Thank you for watching. I hope you enjoyed it and found it useful. If you have any questions, please ask in the comment section. Be willing to answer all questions. Please like and subscribe.